And I love my children. Yeah, who's the third child? Raise your hands. You weren't a disappointment. It was just trouble. Fourth child, it doesn't matter anymore because you gave up. That's me. Oh, yeah, right here. Fourth child syndrome. Okay. So, anyway, when things dissolve, the randomness increases. Sometimes they give off energy, sometimes they take it in. But it's an overall balance. There will usually be an increase between the heat and the entropy overall. All right. You don't have to know a ton about that, but you will possibly have a question. And we'll review it again in chapter 19, where the process doesn't seem to make sense, but it's because there was an increase in entropy. Go ahead.
So you say that entropy will always go. What about crystallization?
Crystallization gave off heat. Like it gave off energy, that energy went into the universe, and overall the entropy did increase. The system may have decreased. And this is, I think, the third law of thermodynamics is that the entropy of the universe is always increasing. We can never decrease it because we'll put in work, that work expends heat energy, which is dissipated.
So eventually the universe will be chaos.
Yeah, but really it's kind of bizarre because outside of any like religious thing, how did a planet come together? That seems like that would never have happened according to the laws of entropy, right? All this stuff was scattered, came together because of gravity. Where was that energy released? Heat. In the collisions and the grouping of the particles. But the order of the universe really doesn't make a ton of sense why it would happen that way. Speaking of the universe, I read an article today. It was really cool. A rocket from whatever, what's Elon Musk's company called? SpaceX, like 2.5 years ago, they lost control of it and it's about to run into the moon on March 1st. Just kabam. And this was cool. They don't know exactly where it'll hit because of sunlight shifting. I was like, that is awesome. That the photons coming from the sun will change the direction of the actual rocket. That's pretty crazy. Space is cool. Random rockets just flying into the moon. Cool. All right. What? No. And sadly, it's hitting the backside of the moon. No. Which in all the cruel jokes of the world, we only get to see one side of the moon every single time we look at it. That's bullcrap. I want to know what the other side looks like. But I don't really have that option to just go to it. All right. Anyway, kind of interesting. Moving on. That rocket will go from ordered to disordered at some point in time on March 1st. That's why it mattered. Okay. I just said all this. So even though enthalpy may increase, that's the temperature or the heat, the overall energy can decrease because the system becomes more disordered. We'll learn a ton about this later. All right, now we've said this before in chapter 1 or 2, but now it's the other direction. Warning, just because a substance disappears when it comes in contact with a solvent, it doesn't mean the substance dissolved. It could have reacted. And you know what? In chapter 1, it had the same slide. It just said the other direction. Just because it reacted or they came in contact doesn't mean it reacted. It could have dissolved. So to know whether it reacted or dissolved, we need to look for evidences of a chemical reaction, which are heat change, unexpected color change, bubbles or gas, smells of gas. Said that one. A precipitate, which is accompanied by a color change. Light, like when you light a match. And then the last one's when you can't see very well, but that's a electrical potential is created. It's a redox reaction where an electron flows. You can't see those very well, but that's what batteries are made out of. All right. So if you see one of those, a reaction did happen. If you don't, it means it dissolved. Moving on. All right. Dissolution is a physical change. You can get back the original solute by evaporating the solvent. If you can't, the substance didn't dissolve, it reacted. Okay, look right here. You can write, but it would seem like we are increasing the order in this, which would be decreasing entropy. But we're not. How do we evaporate things? We have to add energy. Like we can reorder it, but we have to put in the energy to do that. That was my sad face because Ashley was walking down the hall today with the bucket full of hot chocolates, and there was one left, and I was right in front of her, and I stepped over. She's like, "Oh, sorry, I'm giving this to someone important." I was like, "Oh, thought it was Hope Week." My hope is to someday be important. Then she's like, "I didn't mean it that way. Like I already told." I'm like, "I'm just crushed inside." Yep, it was sad. I went and got hot chocolate. I got 2, and then this is TMI, but I got a bathroom like 10 times. So whatever you guys did to that hot chocolate, I'm a little concerned about it. I have had to go to the bathroom. All right, moving on. That was gross. Okay. This is super not AP stuff I'm about to say. If you're like okay with prefixes in words, we're going to be fine. All right. There's tons of different types of solutions, but these are 3 words we're going to use to describe the concentration of a solution. The first one is saturated. Any other guesses what the next one is? Unsaturated. You guys should have learned it. Super saturated. But it means over. So, all right, here we go. So this is a way to describe their concentration qualitatively without numbers, is what qualitatively means. So if you ever hear something that is saturated, it means the solvent holds as much solute as is possible at that temperature. It cannot hold more. All right. So an example of something saturated would be if your car has 5 seat belts, you should maximum carry 5 people. Should. Could you hold more? Yes. Could you hold less? For sure. But if you held exactly the amount that it was designed for, we'd say it was saturated. Now, a lot of you have had bio and you want this to apply to saturated and unsaturated fats, and it doesn't really work. All right. Those deal with single and double bonds, and that's okay. Like I could wiggle it into this, but it is a different subject. All right. Now, we're going to soon move on to a chapter that talks about equilibrium for like a month and a half. There's 3 chapters. So have we talked about a dynamic equilibrium yet? Okay. Equilibrium means that things are in a state where they don't change. Now I'm going to draw this out in a minute. Dynamic, get ready for it, means that they're changing. I love chemistry. Why make sense if we don't have to? Okay. Here's the deal. It means there's a change, but there's no net change. So let me draw it out and it will make sense just fine.
The system might change, but the entire surrounding changes.
You can, that's the way to define it. So look, the easiest way to describe it before I draw it is this room. There are 29 of us in this room right now. Okay. A dynamic equilibrium would mean if 3 people came out, we would send, or came in, we'd send 3 out. So in this room, would we have the same 29 people? No, but we would have the same amount of people. But there's no overall change, really. You with me? Okay, so let me draw this out with something that hopefully most of you will understand. Nope. But close, it is a food. No. No. No, close. Cheerios. These are Cheerios. Now, in my opinion, standard Cheerios taste the same as the box they come in. This is my opinion, and if you don't agree, that's fine, but I'm the teacher and I have the mic, so I will talk over you. Okay? So, for Tom Davidson, to make them bearable, I make them taste like sweet cardboard instead of plain cardboard. No. I would never do that to myself. I pour Mountain Dew on it. Joking. It's pretty honey, or I'm going to say sugar. Okay, now stick with me. I have milk. In this situation, milk is called the what? Solvent. Okay, at a specific temperature, milk can only hold a certain amount of sugar. And if it's holding that amount exactly, we would say the milk is what? Saturated. And if it's saturated, then we would say it's in a dynamic equilibrium, which means the following. If I have sugar on the bottom, that means I'm saturated. I know that because it won't hold anymore. There's sugar on the bottom, which when I make Cheerios, there's got to be sugar on the bottom because that's the only way I'm going to eat it. I'm sorry. Look at my body. Clearly, I'm unhealthy. All right. So here's my spoon. I'm going to get a little bit of sugar and hopefully no Cheerios and eat. Here's the deal. I actually can add more sugar, even though it's saturated. So I take a little thing of sugar and I drop it into the milk. You okay with that? And it's weird, even though it's saturated, it will dissolve. It will break apart. It will start to do that. But this is a equilibrium and it's dynamic, which means if some starts to dissolve at the exact same rate, some starts to clump back up. So the concentration of the sugar remains constant, even though the sugar atoms themselves, molecules, sorry, they might be different ones, but the concentration stays the same. So a dynamic equilibrium means there can be a change, but the overall change is zero. The same, I know what you mean, but I'm going to say zero.
Things can change, but another thing changes at the same time.
Yep. So another example is my bank account. I get around $4,800 check every week, or I wish, every month. But at the end of the year, I'm not 48 times 12 richer, because as some came in, almost the same amount went out. You okay with that? Now I do save money every year, so it's not a perfect equilibrium, but you find a $20 bill and you go pay your book fine at the library. And you're like, well, we have, I don't know, book fines used to be a thing when I was a kid. Maybe they're not to you anymore because you just use your phones and don't know how to read anymore. My fault. Anyway, or you found a $20 bill and you lost it. How about that? Well, someone lost it in the first place. Oh, shut up. Okay. Are you all right with this? Some will dissolve, some will reform. Okay. That happens in a saturated solution. In an unsaturated solution, there would not be any solid at the bottom because it's not holding as much as it can yet, which means it's holding every amount of the solute that I put in. Okay, so there's more space if it's unsaturated. And if I add a clump, it's going to go in and it's going to dissolve. And it will continue to dissolve until it reaches the saturation point, which is determined by the temperature and the substance. Once it hits that, then the sugar starts to clump up at the bottom. So my dad is like OCD. He's not anymore because he's like 80 and doesn't have a care in the world anymore besides his health. I mean, he's an 80-year-old, but he's super weird. You ready for this? He's the only human I've ever known that puts his cereal together in the following manner. He puts milk, he puts sugar, and stirs it until he hears it start to grind. And then he puts his cereal on top. Why? I don't know. His parents grew up in the Depression. I don't know. He didn't want to waste any sugar, but he always took it like right to as much as the milk could hold, and then he ate. Now, Tom Davidson, cereal, milk, so I can make the top mushy, and then a ton of sugar, so it was sugar coated because it was already wet and it stuck to it. Okay, I think I got it figured out personally, but my parents did not grow up in the Depression, so they grew up with depression, but that's different. Okay, not funny. Sorry, not funny. Not funny. Love you, mom and dad. Okay. Yeah, sorry, too soon. All right. Supersaturated is weird to draw. Hold on. Oh no. All right. Supersaturated. What? I'll tell you in a minute. Yeah, my dad's like, I've been following on Zoom and I was not depressed. Like, oh, why did you drink alcohol all the time? Sorry. Sorry. True story. My bad. It was probably for his fitness. Okay, I gotta be better. Davidsons have drinking problems. Gets better every second. All right. Okay. Supersaturated is holding more than it should at, that's an at sign, a specific temp. It breaks the rules. Now, supersaturated, it takes a specific process to do this. It's not real complicated, but it takes a very specific process to do this. What you do, I probably have a slide on it, but we'll draw it anyway. What I do is I add heat. Right, just stick with me. Don't fight me yet, okay? I get it really hot and I add a ton of solute. Okay, I add a ton of solute to this hot liquid and all of it dissolves. You okay with that? Then I turn the heat off and I let it cool without doing anything to disturb it. Okay, like I can't even, like if I went like this, boom, it's going to turn solid. If I add a little bit of solute, it's going to turn solid. I have to let it cool slowly over time. And without any disturbance, it will stay a solution. But if I add even a tiny just piece to the whole thing turns solid. And I'll show you a video. Now, everyone says, why don't you do this in class? Sometimes I do, but it's extremely temperamental and usually doesn't work. I've done it. I know that I'm a failure.
Why'd you have to say that, Corbett?
I'm fine. It started with Ashley and it's just been a downhill slope ever since.
So we have a supersaturated solution. There's more that can.
Okay, here we go. I have not previewed this video, but I assume it's already been heated and cooled. And now he's going to add the seed crystal, which can be like literally 1 sodium chloride. It's most likely sodium acetate, because hot liquid will hold like 5 times the mass of sodium acetate than the mass of the solute in the first place, or solvent. It's really crazy. You'll have that much water and like that much solid, and you heat it, and now it's a liquid. You're like, how does this work? Science. Okay, so I don't know, and I never like playing the audio. Okay, there it is. I guarantee that's sodium acetate. All right, let's go, bro. Okay, we'll take it right there. Okay, so he's about to drop it in. He drops it in, and what you're watching is the solute come out of solution, because it shouldn't have been able to hold as much as it was. So it turns to a solid. Now, I got a question for you, just common sense wise. If I'm going to come over here, if I touch this right now, tell me what I'm going to feel, heat or cold. Tell your partner, actually. It's probably Daniel Matheson. I guarantee it is.
Okay.
Okay, what do we think? Is it going to be cold or hot? Who says cold? Raise your hand. Who says hot? Who says there's not enough data? Okay, the answer is really hot. It would burn you badly. Yes. Okay, I did. So, what did I have to do to get this to dissolve? I had to put a ton of heat in. It was dissolved, and now it quickly goes from dissolved to solid. Like, it probably took 20 minutes to heat and dissolve this to get it to work, and then it went solid in 10, 20 seconds, right? All the heat you put into it to do that process has to be released in the reverse process. So it's a really exothermic process. All right. Well, that's that. So it's not super saturated unless you've heated it, added excess, and let it cool. It takes a lot of things to get it to be super saturated. Okay, most likely the next slides say the same thing. Unsaturated, wow, same picture. Oh, I forgot to put the holes in the whatever. All right, it could hold more. There's more space. Easy enough? Okay, super saturated, same thing. The solvent holds more solute than it normally possible at that temperature. These solutions are unstable. Crystallization can occur, usually be stimulated by adding a seed crystal or scratching the side of the flask. What's that?
Is this how snowflakes were made?
Snowflakes? No. It looks like a snowflake. The closest thing that you've actually done with this is if you've ever made rock candy. That is so much fun. And it's this. Because you heat water and put in a ton of sugar. Put a stick in it, and that's the seed crystal that the oversaturated thing, as it cools, it sticks to and makes your like very crystalline rock candy. I'm sure that it absolutely matters. You would need something porous to give it, like, it's called the nucleation site, if you've ever heard that word. If it's plastic, it's just smooth and there's no real place for it to stick. It's why Mentos are so good at making Diet Coke explode. Because if you ever lick a Mentos, it's like 200 grit sandpaper. Like, it's not perfectly smooth, but I can drop an M&M in there and nothing happens. Okay, so it's because Mentos have thousands of millions of nucleation sites where a bubble can form. And then they are like, oh, I can get out of this solution. Boom, they're gone. So the type of stick would probably matter for the same reason. You give it more places for the seed to actually stick. Good question. Did you end up with just a bowl full of hard sugar? Stayed liquid. Yeah, I'm picturing my daughter Carly being super excited and like, oh, another Dutch. Speaking of my sweet daughter, I have a pile of papers right here she made for me last night. Yep. I got home and my wife had made lasagna, which is like one of my top 3 favorite meals of all time. And I opened it and I took the tin foil off, thank you. And I looked and I like died inside because yesterday I had the worst heartburn of my life. And I ran with my track kids. And it was like, I swear it was in my ear hole. Okay. And I was absolutely dying. And so I get home, I'm like, I want to eat that so bad, but I know I can't. And Carly, my amazing, kind daughter, she's like, well, why do you get heartburn? And I'm like, it's from soda pop. I'm not sure how it gets into my body. And so she kind of laughed. So then she asked me about my addictions. So she made me these signs. 1 pop a day keeps the heartburn away. She doesn't understand me. She made make a bet for a good grade, no pop. She thinks that you guys can dare me to not drink and somehow that gets you extra credit. But it's the reverse. No more pop. Saying 1 a day keeps the heartburn away. Make a bet to get a good grade. No more pop. Whatever. Only 1 pop. She's like, you got to take these to your work and put them up. So I've only had 2 today. But I drove this morning. You can't drive at 5:30 in the morning and not drink caffeine. I'm sorry. Yes, it affects me. I'm happy with it and not without it. I sound like an addict. Okay.
Your loved ones are worried about.
Yes, it's affecting my family. That's like step 5 of addiction. Trust me, I know. Okay. I'm sorry. This isn't really that funny. No, I'm fine. I can drink. I can handle it. It doesn't control me. I control it.
Okay.
Okay.
Intervention.
Says the girl with an energy drink.
Second one.
Got-
It's because of this class. I go to bed like 12:30 because I
Mhm.
was studying for the test.
Mm,
You're saying this class is boring?
Yes, that is exactly right.
no, she was studying. Okay.
Not only are you you're making your students get addicted to something.
How? I just told you how bad it is for me. It like burned my throat, like I've been coughing all day because of acid reflux. And announcing basketball games with mad heartburn, I like it sounds dumb, but it like sucks. But it's okay. Are we ready? All this is on the internet for any loser that finds my channel to hear. Okay, factors. This is important. Factors that affect solubility. There's not a ton of them, but chemists use the axiom, which is just a cool word for saying the saying, like dissolves like. And that's really easy to understand. It means things that are polar dissolve in polar substances. Things that are nonpolar dissolve in nonpolar substances. And typically, they don't mix. So that's why your Italian dressing, you have the water on the bottom with all the flavor, then the oil on the top. And if you're like 10-year-old Tom, you don't shake it and your salad's disgusting. Okay, so, and that's because you have a nonpolar substance with a lower density on top of a polar substance with a higher density. And most of our salts and flavoring agents, they dissolve in water or polar substances. So 100% all you get off the top of your Italian dressing is just the oil. You have to shake it or it's disgusting. Okay, there's your life lesson for the day. Hey, just an FYI, my dad was not an alcoholic. I've just been joking. He did enjoy a beverage often. And he currently is in Alcoholics Anonymous, so maybe he was, but he hid it pretty well. But you know, my dad was like a great dude. Don't even worry about it. Yada yada. Moving on. Okay. So here we go. This table, don't write it down, but methanol is infinitely soluble in water, but not infinitely in C. Is that a 6? All right. So what would that be? Hexane. Good. Okay. Sorry. All right. You don't have to know that, but let me talk about it. So propanol, look at this. It's essentially infinitely divisible, not divisible, but whatever, in both. That makes no sense, except for, what does it have here? An OH, which would be a polar bond, right? But attached to it is a medium-sized carbon-hydrogen chain or alkane. So it's the middle. These two are the middle ones right here. I've been pointing at that one. These two kind of can do both because they have the hydroxide or hydroxyl group, and then they have their nonpolar, which are just van der Waals forces, right? Okay, but then they switch and yada, yada, yada. Okay, just know like dissolves like. So when I was a kid, I worked at a grocery store, and in the like the wet, what do we call it? Anyway, the one, the sprinkler spray, you know what I'm talking about? We wanted signs to tell their prices, but the water, you can't use like a marker here, but you still have to change them. So what we would use, we had a plastic sign. Okay, I'm still in highlighter tool. And we would write the price on it, like 94 cents or something like that for whatever. Nothing's 94 cents anymore. But if we needed to change the price, this was written in permanent marker, which really means it's written in marker that doesn't wash off in water. So it was really odd, but we had hairspray that we would spray this with called Aquanet, and it would just like roll off the bottom. It was really cool because the marker and Aquanet were almost the same exact material. So the Aquanet dissolved the marker immediately and it just dripped off. What? They still make Aquanet? It seems like it's from like the 20s and causes cancer in California. All right, good enough. So permanent, nothing's permanent as long if you can find the right solvent. Back like forever ago, this was really cool. They came up with something called carbon tetrachloride, which we've talked about before. It is C 1, 2, 3, 4 what's? Cls. Carbon tetrachloride. Carbon tetrachloride is a really heavy gas at room temperature. And someone figured out, and I don't know who, they figured out that it was an extremely good solvent. And they demonstrated it for using it in dry cleaning. And you could go into like a little pool of it with your clothes on and walk out of it and all the crap was gone.
What?
It would be left at the bottom of this pool, which was a gas, by the way. What the crap? That's pretty amazing, is it not?
Yeah, that's gonna make some.
There's only one problem, and every other state. It's extremely toxic, and they didn't know it at first.
Wait, does that mean they put someone through it?
Yeah, people, every time there's like new science stuff, someone's probably gonna die. Yeah, x-rays, I told you about x-rays and like how you could try your shoes on, right? They never got cancer, like, sorry. Yeah, so yeah, but really good solvent. The Hill Air Force Base used a solvent called toluene for years to clean stuff. And they would like clean all the stuff, they get all the waste and they just dump it on this hill. It's not toluene, it's something else. It might be toluene. Anyway, so here is, no, it's not radioactive, but here is Hill Air Force Base. It's on a hill. They dump toxic waste that they don't realize is toxic. It gets into this dirt and it's super small. All right, and pretty dang soluble. That's why it dissolves things. And it goes down over time until it got into the water table. And here's the freeway right here. Okay, this is I-15. And there's a big, you'll see it someday. It's not huge, but there's a canal right here and a ton of dirt that's been removed here to try and get this toluene from like the 1940s out of the groundwater because it's toxic to the people down under. What?
Isn't the canal still there?
The canal's still there, everything's still there, but most of the dirt's gone.
Yeah, I remember I watched like the movie about this and stuff happened with like the stainless steel like cans or whatever that had like the coating on it and
Mhm.
like super slippery and
Yep.
like getting in the water.
The Teflon, it's like TX something, that's the main component. Yep. It's cool, like tons of awesome chemistries involved. And then eventually they're like, oh yeah, and that'll kill you. So sucks to be a chemist nowadays
Water soluble in anything?
in any polar substance. So, oh, is there a bell?
Yeah, it does.
Oh, we got 2 minutes. That's like forever. All right. So things that have hydrogen bonding dissolve extremely well in things that have hydrogen bonding. So sugar does not dissociate. You remember what that means? The CH's and O's don't break apart themselves, but a sugar molecule and another sugar molecule are extremely soluble in water. They don't dissociate, but they dissolve. There's a big difference between those two things. Ionic substances dissociate into ions. Polar substances break apart into just smaller versions of themselves. All right, whatever. We don't need these examples, but okay, we'll pick this up here tomorrow. Okay. Whoa. You have two options. You have three. I'll be fair. Who needs to finish the test? Raise your hands. Okay, a lot of people do. That's the number one goal today, is to finish the test. You listening over here? Okay, finish the test. The number two goal is we're not really doing anything. But if you're bored, we're gonna spam that track vote for Kylie Hadfield.
Oh, I already did.
No, I tried. I couldn't find it.
It's kind of weird. If you actually click on the link and it's Latin. Hold on. Hey, I need that for a minute. Well, I don't need it, but I need you to not do it. I need you off of it. I've never stopped this recording.
I voted for Kylie.
Hey, I need the mouse. I need it. Oh my laws. You can't leave it on there.